So welcome back. Things other than material. The fifth problem set is due not on Wednesday but on Friday because I figured you all didn't want to do it over the break and to give you enough time to get it settled. It's on magnetism in general. Material we've already done, so it shouldn't be a problem. I mean, you should be able to do it anytime. One thing that I didn't talk about that I will mention associated with the problem set is that if you have a compass needle in the Earth's magnetic field, it tends to align with that field because a compass needle, like all magnets basically, it has no net pole. It has a north pole and a south pole, but it has no overall pole. It isn't pushed very strongly by a magnetic field. What do I mean by this? A positive charge is pushed strongly by an electric field. That's what electric fields do. They push on charge. So the positive charge just goes off it goes. Magnetism is different because no object we've ever seen has a net pole. So if you had a north pole by itself and put it in a magnetic field, it would be pushed. That's what magnetic fields do. But since you never find a north pole without an accompanying south pole, there's a battle going on. The north pole is pushed in the direction of the magnetic field. The south pole is pushed opposite the direction of the magnetic field. They're fighting each other. And what that tends to do is align the magnet, the dipole magnet, with the field. It tends to go north pole in the direction of the field, south pole opposite the direction of the field. But the two poles don't, if the field is pretty uniform, that is, it's the same all over the place, same field here as here as here as here, which is true of the Earth's magnetic field. The Earth's magnetic field here and the Earth's magnetic field here are negligibly different because the Earth's so big and everything's so uniform. If you've got a uniform magnetic field, the north pole is pushed in the direction of the field, the south pole is pushed opposite direction of the field, they fight each other, there's no net force on the compass needle. Is that okay? The idea that compass needles don't get pushed very strongly, or for all practical purposes, they're not pushed. No force due to the Earth's magnetic field. Just an orienting twist, a torque. All right? But if you do have a strong magnetic field that's not constant, that varies from place to place, well then a compass needle or any other magnetic dipole, a bar magnet with a north pole and a south pole, it will tend first off to line up with the field and then get pulled into the strongest part of that field. Because once it lines up, wherever the field is stronger, it will have a bigger influence on its local pole. So if the north pole and the south pole are as far apart as my hands, if this pole is in the stronger field and this pole is in the weaker field, the stronger pole wins. It's going to get pushed harder. They don't cancel anymore. The result is that when you have magnetic dipoles in a field that varies over space, magnetic dipoles tend to get sucked into the strongest part of the field. Because the dipole near there gets the strongest push. If instead of a compass needle, you have just a piece of iron, which is potentially a dipole magnet, but normally is that's hidden by this effect where all the domains are random. If you put that piece of iron in a strong magnetic field, that also varies with location. First off, the strong magnetic field will polarize the iron. It will develop a north pole and a south pole because its domains will no longer cancel. And then it will seek the strongest part of the field because the pole in that region will get the strongest shove. And that's why, for example, I used to have that big horn electromagnet up there with a big chunk of iron. Why does the iron get just pulled like crazy against any of the poles? It's because the strong magnetic field around that electromagnet, when it's turned on, polarizes the iron, and the field isn't uniform. It's strongest right near those poles. And so the piece of iron becomes a magnet, and then it seeks the strongest field. Whoomp! Goes against the pole. Is that okay? That's important to one of the problems on the problem set, that concept that a piece of iron actually tends to, it magnetically polarizes and tends to be strong field seeking. And it's not only is on the problem set, but it's really important in lots of devices that are electrically actuated, that some electrical thing causes something to happen mechanically. A lot of the times it's that, an electromagnet yanking around a piece of iron, making it, magnetizing and then pulling it into the strongest part of the field. You can do all kinds of interesting things with that particular mechanism. All right? All right. Where I am in the content of the material, kind of the course really, is talking about electric power distribution. And I'm close to done, but I want to make sure I convey a few key ideas because they're not easy, not obvious. You can't see them, and I don't want them to be mysterious for the rest of eternity. I try to get them across to you. What we've seen up until now, in effect, is there's a world of electricity where electric charges and things with electric charge, like an electron or a proton, they create electric fields. Right? That was the original source of electric fields, where, again, electric fields are this structure in space that pushes on electric charges. In the world of magnetism, same idea. There are magnetic poles, and they create magnetic fields, which in turn push on magnetic poles. The peculiarity is, of course, is that we've never found an object with a net magnetic pole. It's always pairs of poles or more than pairs of poles. So the overall pole is 0. Okay, but other than that, they're very similar. Where these two worlds began to interact with each other is really with time. As things change with time, change allows these to talk to each other. And the first one that showed up, the first such relationship that showed up is if you have electric charge that's moving, which we call a current. So a current of charge on the move. It's magnetic. It creates a magnetic field. So you don't have to have any magnetic poles around to create a magnetic field. You can make a magnetic field just by moving charge. So far, you okay? It turns out the same is true with magnets. Moving magnetic poles create electric fields. I showed you that. I don't have the gadget here this time. I showed you this with moving a magnet around near a coil of wire. It lights the wire up. It lights the bulb up, not the wire. Okay? So moving charges are magnetic. Moving poles are electric. Whoa, this is pretty good. This allows for more complicated relationships, like a current itself is magnetic. A current that changes with time, not a steady current, not the steady current in a flashlight, but a current where you turn it on and off and on and off. That's now magnetic, and it's magnetic changing with time. And actually, to lead into this, I should add one more idea of change. Let me rewind for a second back to this idea that moving charges are magnetic, and moving poles are electric. The thing I left out is not only is moving charge magnetic, but changing electric fields. And this is actually a new statement. Changing electric fields are magnetic too. A changing electric field can create a magnetic field. What is not new, and I've said last time, is a changing magnetic field creates an electric field. So basically anything that changes magnetically, any magnetic thing that changes is electric. And any electric thing that changes is magnetic. Is that okay? Now where does all this go? It means that you can do these multi-step things, where if you have a current that is changing with time, so a current is magnetic, but if the current changes with time, not only is it magnetic, but it's magnetic that's changing with time. Oh, a magnetic thing that changes with time is electric. It's a double step. The electric thing, namely the current that's changing with time, creates magnetism, which in turn creates electric effects. There's an electric field that is due to the magnetic field that's due to the current. Back and forth, it's hard to follow, but hopefully you can get that basic. Let me show you that. I've done these things before a little bit. This is a coil of wire that connects directly to the power line. There's a switch in it. Right now, no current's flowing. Now there's current flowing. You hear it humming. What you're hearing is that current is not a constant current. like all things associated with our electric power grid, the current is going first one way and then reversing. That reversal is smooth, it's sinusoidal in time, as associated with the sine function, sine of time. And so that current's going first one way, then the other. Well, currents are magnetic. So this guy, this chunk of iron, in the presence of this, even if I didn't have the iron, there would be a magnetic effect here, basically a magnetic field, and it's a magnetic field that would be changing with time, because the current's changing with time. The iron amplifies the effect, because that magnetic field magnetizes the iron and really boosts the intensity of the effect. So what you're hearing humming here is this chunk of iron is being magnetized first north pole up, then north pole down, north up, north down, and there are forces associated with the fields interacting with the iron and the current in this coil and the iron. They're pushing on each other, and the pushing is pulsing on and off as the magnet flips, and so it buzzes. And you can hear the buzz? That tone, you've heard that tone countless times in your life. It's associated with all sorts of gadgets that plug into the electric power grid and have these magnetic and electric interactions with each other, and they fight each other and they shake. And they buzz at this frequency. It's part of life. It's a nuisance, but it's there everywhere. Familiar, I hope? Okay, so the magnetism is going back and forth, back and forth. But I told you, a magnetic effect that changes with time is itself electric. It creates an electric field. The relationships between the electric and magnetic fields and stuff are complicated because electric fields are vector fields. They have direction with them, not only amount, but direction, right? Magnetic fields, amount, and direction. So these are directional things interacting with each other by way of changes in time. And getting the directions right is a nightmare. I mean, physicists can do it. We've got a whole mathematics for dealing with it, vector calculus and stuff like that. It's a messy thing. You don't need to know it. What I can tell you is that the changing magnetization here, up, down, up, down, up, down, that magnetic field fluctuation, creates an electric field that circles this piece of iron. It circles it first one way and then the other way. And because it's circling it first one way, it will push any charge that's in this area. It will push it in its direction, like it would love to push it around in a circle. And if the charges, of course, like all objects, tend to be inertial. They want to go straight. Going around in a circle is kind of tough. You've got to guide them to go around in a circle. But if you put a piece of metal, so this is just a piece of aluminum, no batteries, it's the world's simplest circuit. It's a circuit. Charge can go around it and come back to where it started. But how would you ever get charge going? Well, the way you get charge moving in it is by putting it in this crazy changing magnetic field, which creates an electric field. An electric field will push charge around that ring, first one way and then the other way, and back and forth. And the result is the ring becomes magnetic. It itself ends up with a current. And the current is magnetic. There's a magnetic interaction between this thing's magnet and this thing's magnet. They push apart. There are other ways in which to describe why this guy jumps. It's not a trivial story why it jumps up like that. But you can see the basic idea that current does begin to flow in this. I can also show you the current with this coil of wire and a light bulb. There's the current flowing in it. This, I hope, would remind you, many of you will have an electric toothbrush that's cordless. It plugs into a base. It just sits in the base, and somehow that magically charges it. What are you doing when you're landing your toothbrush in the base? You're assembling this kind of structure. The base has this fluctuating electromagnet, and there's a coil of wire in your toothbrush that has charges pushed around it. Any questions about this so far? Just for giggles here, you can see that guy will jump to about here when it's at room temperature. Aluminum is a pretty good conductor of electricity. Copper is a better conductor of electricity, but it's also very dense. It's heavy for its size, so it doesn't jump as well. But you can make the aluminum jump better with everybody's favorite random thing to bring out. Oh boy, liquid nitrogen. My standard cliche or something is any excuse for liquid nitrogen is a good excuse. So there's liquid nitrogen, which is about 1/4 of room temperature on an absolute scale. It's really quite cold. So we make the aluminum go swimming in there. And I talked about conductivity of metals, that metals are typically relatively good conductors of electricity. They don't allow charge to coast because the charge tends to hit things. And the things that it hits microscopically within the metal are, I mean, they're sort of at the atomic scale, and they're often they're bumping into things that are jiggling because of thermal energy. If you can cut down the thermal energy in a metal, you can improve its electrical conductivity. So cold metals are better conductors than hot metals. There are other materials that have the opposite effect, but for metals, cold is good, hot is bad. Oh, come on, what's up? Okay, you're cold, finally. All right, so now it's nice and cold. You know, it's a much better conductor of electricity. It's also quite cold. Yeah, anyone want to come up and touch this with their tongue? Yeah, you know, the world's worst version of that example. Okay? So you can see currents are being driven through this chunk of metal by an electric field that's not produced by charge directly at all. It's produced by a changing magnetic field. Where does the changing magnetic field come? It's not produced by poles at all. It's being produced by a changing electric current. So we are really mixing and stirring the world of electricity and magnetism. Any questions about these things that are tough to follow, that you'd like me to do again? So this is basically a transformer. I've talked about transformers a little bit, and the other day I talked about them. We're taking electric power from the power grid, going through this coil of wire. We're conveying it by way of a fluctuating magnetic field to a second circuit, completely independent of the first circuit. No charges are passing between these two circuits. One of them includes the power grid, and one of them is just isolated. It's a little world of its own right there with a light bulb in it. And power is moving through the electric and magnetic fields between these two things. Okay? One more thing to show you with respect to this. Magnets, changing or moving magnets, produce electric fields. And electric fields, when they have the opportunity to push charge around, tend to cause the charge to flow. They create currents, and those currents tend to be magnetic. So if you have a moving magnet near something that can conduct electricity, the moving magnet tends to cause electric currents to flow in the thing that's nearby. It's a multi-step idea. The moving magnet creates electric fields. The electric fields push charge around, the charge moves and becomes a current, which is itself as magnetic. Is that okay? There's a law known as Lenz's law there at the bottom. And I should say, that effect is known as generically as induction, that you can induce currents by changing magnetic stuff. Changing magnetic stuff will create the electric field, which will push charges around and will cause which will cause currents to flow, which are themselves magnetic. That's called magnetic induction. You're inducing currents just without a battery. You're making them happen because you're playing with magnetism. The currents that flow are themselves magnetic, and they tend, according to Lenz's law, they tend to oppose whatever it was magnetically that made the current flow in the first place. So, for example, and that's where I'm headed with this. Where's the open? Okay, here's one of these super magnets. This is a big guy. This guy's dangerous. We've had fun with this, but they make them bigger than this. This one's already like, you don't want to get this anywhere near a chunk of iron, because it will polarize the iron and then stick like mad to it, and if your finger's in the way, sorry. You now have the world's biggest, flattest finger. This is a big chunk of copper, very good conductor of electricity. It's dense, it's heavy, so we won't lift it. We'll just let it sit here on the desk. And if I drop the magnet just on a piece of, on the desk, you know, it just falls. Actually, it finds a chunk of iron in that desk. It wants to stick, but okay. But copper is not a magnetic metal. That is, it's not ferromagnetic. It has no magnetic microscopic structure, nothing there. But if I drop the magnet on the copper, watch what happens. It doesn't drop properly. It's trying not to. It falls very slowly. Ooh. This guy's heavy. There's nothing wrong with gravity. It's falling slowly. What's going on there? It is, as it descends, it's a moving, changing magnetic field. It creates an electric field, causes currents to flow in the copper. That's why we chose copper. It's a great conductor of electricity. The currents that are flowing in there are huge, induced by that moving magnet. Those currents flow, and they are themselves magnetic, and they fight the change that created them, namely the approach of the magnet. It's hard to make that magnet. You have to push the magnet, and you can try this after class. I'm trying to shove the magnet against the copper, and I can feel it fight me. It says, no, you can't come in here. Lenz's law. If you're trying to make the magnetic field increase into the metal, no, we'll fight it. You can't do that. And if you try to pull it away, it fights you on the way out. Fights on the way in, fights on the way out. It's both directions. And actually, if you go around in a circle, it fights you like crazy here. And this is, and these effects, they're used in various devices. They're used to damp out vibrations in certain instruments. That induction of current in the magnetism that results, because it just fights motion. Questions about that idea? So you're welcome to try this after class. Keep this away from anything to which it will grab, because it will grab hard. All right? All right, well, I want to jump ahead now to I've talked about transformers at this point enough, and if you didn't see it, go look for it in the book. It's, I can do it in the book better than I can do it live because I have all these animations associated with the electric and magnetic fields and currents and all that stuff. Okay, so the big story, the reason that the overarching topic, if you remember, was this observation that if you try to send power long distances with ordinary wires, unless you make them crazy thick, you lose an awful lot of your power en route. So there's the local light bulb, and the distant light bulb through these skinny wires. The distant light bulb, pretty measly glow there. The reason for that is because we're trying to convey power using a large current of charges that have a relatively small voltage drop available to them. Each charge doesn't have very much energy to drop off, so we end up needing a large current going through those very thin wires. They lose a lot of their power. They waste a lot of their power simply going through the wire, making the wire warm. So far, any questions? Yeah, I'll keep asking. You can keep ignoring. Okay, what's the alternative? I mean, I showed you thick wires will work fine. That's the simple-minded way of doing it. The better approach is to use a pair of transformers. Leave the battery. Get rid of the battery. Instead of using the battery, let's use a fluctuating current, an alternating current. The standard in the U.S. This current that reverses direction every 120th of a second. It reverses direction. So 60 full cycles of reversal every second. We'll shift over to the alternating current. The light bulb doesn't care. It'll glow just fine if we run current through it AC. And I can show you that. Let me start with that. We'll shift over to AC. The AC that I'm going to obtain comes from the power line. Ignore this. There's a transformer here just because I want to work with the same voltage as I worked with the battery. It's a 12-volt battery. This is 12-volt AC, which isn't available from the power line, but we create it with this transformer. And so that battery, that AC lights up the light bulb just like before. The distant light bulb is dim just like before because we're still using the same voltages, the same wires. The only thing that's changed is that we've got this strange current that reverses direction. Otherwise, pretty much everything's unchanged. So we have not solved the problem yet. How do we solve the problem? Instead of using a large current with a small voltage drop available to it. So each charge has a small amount of energy to drop off. Let's go through a step-up transformer. So we'll take our 12-volt AC, and instead of sending it a long distance, sending power a long distance as a current of 12-volt AC charges, we will go through a step-up transformer. The charges will not go from one circuit to the other, but we will take power from one circuit and convey it to a second circuit at much higher voltage, somewhere in the hundreds of volts, the way we've got it rigged up here. And so the power will now be moving in the second circuit, a circuit that lives only between a pair of transformers and has no other access to the outside world. This circuit will be a high voltage circuit, a couple hundred volts, with a small current running through it. You only need a small current to convey power when the voltage difference is big. So here goes, I'm going to take, I'll leave that in there. The local light bulb, I'll leave it in. Here's the step-up transformer. So I'm taking the 12-volt AC power, I'm putting it into the primary coil of the step-up transformer. It goes in here. These wires are associated with that connection. The secondary coil, which will receive power from the transformer, it has many turns in its coil, and therefore it will operate at a much higher voltage rise. And so I will get the high voltage. There are a bunch of different choices here. This will work fine, I think. Okay, so this will now be operating with a smaller current at higher voltage. I will now take the wires here, and I can't run them directly into the light bulb. I need to go through a step-down transformer to undo what I've just done. And it's going to go, so that we've now connected to the many-turn coil, the primary of the step-down transformer. These wires now are part of a middle circuit that connects to nothing else. It connects to the primary, the secondary of the step-up transformer, the primary of the step-down transformer, and nothing else. So the charges are trapped forever going around this little circuit. And finally, the step-down transformer's secondary will provide us with 12-volt high current. Now when I turn it on, yay! It worked. So we have power. The power really is going through these skinny wires. I gotta be a little careful I don't give myself a shock. It's going through these skinny wires as a small current with a big voltage difference between the two wires. So this is a 12-volt circuit. Lots of current, only 12 volts difference between the two wires. This is a 100 plus volt circuit with a small current in it. The third and final circuit is back to 12 volts, big current. And the power is moving from circuit to circuit to circuit. No charge moving, just the power. Is that okay? In the real world, I mean, this is a couple hundred volts. In the real world, to send power any reasonable distance, they go way above 100 volts is boring. They actually, they go up to 1,000. The local city circuits are several thousand volts, maybe 8,000 volts. If you get into the circuits between major portions of a city, they're up in the 50,000 volt range, and if they're going across country, they go up into the hundreds of thousands, maybe even a million, to try to cut the amount of current they're sending through the wires. The need to move power from circuit to circuit explains the existence of these transformers. And if you look around and start paying attention, you'll see them all over the place. What else about these things? This whole electric power grid dates back to the late 1800s. It was not developed with any great planning, which is why it has a lot of flakiness as things go bad in it periodically. It gets overloaded. During your lifetime, it's likely to get some significant overhauls. Maybe out of necessity. It's very hard to get much initiative these days for people to actually spend money on hardware. But but there may be things that just have to happen. And one of the things that might possibly happen is the electronics has developed so much since the era of these transformers and so on, that converting direct current into alternating current, basically moving power from a direct current circuit like a battery circuit to an alternating current circuit like that of our power grid, that moving the power between those two has become enormously easier than it was even 30 years ago. It's no big deal now to have, you can get a solar power system on your roof of your house that is inherently a direct current system. The solar panels always have one higher voltage terminal, one lower voltage terminal, and they use the sun to add energy to charges that arrive in the low voltage terminal and come out the high voltage. So the current's always going the same way through the solar cell. But if you're connected to the electric power grid, you've got to send the power out or interact with it using alternating current, because the power grid is inherently an alternating current system. And so the converters between these, they're often called inverters. They used to be horribly complicated, and now they're just trivial. So moving power from the DC to AC, AC to DC, your cell phones and stuff, you plug them into a charger, the little chargers that go into the wall and come out as USB power, right? 5 volts, direct current. It's a little gadget like this now. Costs nothing. I mean, they're practically free. And so anyway, the ability to convert between direct current and alternating current, and to move between one voltage and another, all based on, in part on electronics and part on transformers, will probably change how the power is distributed over the course of your lifetime. It could easily be that the long distance, the long haul power lines stop being alternating current and become direct current. Why would you do that? Because alternating current, first of all, it has moments when there's no power. The voltages between the two wires, if I illustrate them with my hands, they're doing this. So this one's high voltage, that one's high voltage, this one's high voltage. First of all, there's a moment of zero. That's not good. And they have to go to balance, to maintain an average power that's large. When they've got moments where there's nothing, they have to go extra big. So the power grid, your outlets that are nominally 120 volts AC, if you actually look at the voltage difference between those two wires, on a certain type of average, it's 120 volts. But at any given instant, it can be 0, and it can be as much as 170. It's actually bigger than 120 by multiple of the square root of 2. The reasons don't matter. But so actually the voltage gets higher than it's stated, which is a little bit of a safety issue, but also in those long distance power circuits, if you've got a 1,000,000 volt power line, that actually means that it peaks at 1.4 million volts when it hits peak voltage. And the peaks matter because that's when sparks occur. So they're limited in voltage by the peaks. And so if instead of doing this with the voltage, back and forth, they could just hold it steady, they could eke out some more. They've got some more room to move. First of all, there are no moments of zero power, and the other thing is that they don't have those spikes, those peaks to worry about. They can get a bigger voltage difference, and so I think there's work on super high power, super high voltage transmission systems that are direct current instead of alternating current. So watch it; it'll probably happen. Yeah. Yes. 100 volts. Yeah. Yeah. So the question is the voltages across this system. This transformer's job is to take power in at 12 volts. Voltage difference between the charges arrive at positive 12 volts and they leave at 0 volts. It's a voltage drop of 12 volts at the entry to this transformer. At the exit of this transformer, it provides a voltage rise. It's a source of power, so it's a voltage rise. It's imitating a strange battery. And the voltage difference between entry and exit isn't 12 volts anymore. It's like 120 volts. is much bigger. So each charge that goes through, wow, comes out with 10 times as much energy as the charges that dropped off the power. So you only need 1/10 as many charges per second going through these wires, to carry all the power that arrives through these wires. 10 times the voltage, you only need 1/10 of the current. So the current here is much smaller. And remember that the wasted power goes not as just the current, it goes as the current squared. So reducing the current by a factor of 10 reduces the wasted power by a factor of 100. It's a big effect. And so the power goes over here as a trickle, just a little flow of charges carrying a lot of energy. They drop off their energy in this step-down transformer. They drop off a lot of energy per charge, not many charges, but a lot of energy per charge. So there's a fair amount of power working its way through the electric and magnetic fields inside this transformer. And that energy is transferred to a large current in which each charge only receives a small amount of energy, 12 volts in voltage rise at the output of this transformer. Is that okay? Any other questions like that? You might as well understand this. What you're looking for, if you go looking out in the great wide world, Charlottesville, if you go looking around at power poles, for example, near the university, or the green boxes, it's harder to see with the green boxes what's going on. There are boxes all around these buildings that are, mostly it's hard to see the electrical connections. But the power pole transformers, you can see the connections. Go look at them, and what you'll see relatively thin wires coming in from the high voltage wires. So the power pole will have a couple of high voltage wires sitting on glass insulators. They're at high voltage. Insulation becomes tricky at high voltage. You got to be careful. You got to be careful about animals getting into them. So they're all rigged trying to keep the squirrels from having a bad experience. So you'll see the high voltage wires. You'll see a wire come off the high voltage wires, possibly through a switch so that they can disconnect them, and go into one of these gray cylinders, which are the transformers. They're about this big around, about that tall. You'll see the thin wire come in. That's going to be the part of the high voltage circuit. And then you'll see one or more, a couple of wires coming out of the transformer that are much thicker and typically insulated at this point. The wires going in are, the high voltage wires, no insulation. They're just open, bare metal. The power coming out, much thicker wires and much lower voltage. They're carrying a lot of current now. They have to be thick. They're going to go around where people are. They got to be insulated. And so you'll watch those come down, for example, come down the pole and go into somebody's house, or into some. They may run through the air, but they'll be carrying the. So that's equivalent. What you're seeing is a step-down transformer, conceptually like this guy. The high voltage circuit will go in one end. The low voltage circuit will come out in much thicker wires and get its job done. Okay? Any other questions about power delivery in general? Yeah, so there are a lot of nuances and other things, complexity to it, but that's the basic story. All right. I'm going to leave electric power then, power distribution, and shift over to the next step, radio. And radio is, I view this is the story of electromagnetic waves. We've seen that charges make electric fields, poles make magnetic fields, but they can cross the boundary if things are changing with time. So currents, that is moving charge, changing electric fields, both of them are magnetic, and moving poles and changing magnetic fields, both of them are electric. Well, the fact that changing electric stuff can create magnetic stuff, and changing magnetic stuff can create electric stuff, offers the possibility that a changing electric field can create a magnetic field, and if that magnetic field is changing, right, it can create the electric field, which can create the magnetic field, which can create the electric field, but back and forth and back and forth. You can make a structure that finally doesn't involve any magnetic poles or any electric charge. It's just the two fields, electric and magnetic, making each other. It's like I should get the Escher picture of a hand drawing. What is it? Is it a hand drawing? The hand that's drawing it. I can't remember the picture exactly, but it's like it's self-creating. And that does happen. So my introductory question here is this one. If you shake an electric charge up and down rapidly, so suppose I've got a little positive charge. Do I have my charges with me? Maybe. Yeah, I do. All right. So I got a positive charge, and I shake it up and down. Clearly, if I've got a piece of metal nearby, if I have the positive charge up here, it's going to polarize the metal, right? It's going to pull the negative charges near it. And if I move it down, it's going to pull the negative charges down toward it, obviously affecting the metal here. The question is, how far away can that metal be and still be affected? Okay with the question? How many think it'll be 1 meter? How many think it'll be at 1 kilometer? How many think it'll be the other side of the universe? Yeah, it's the other side of the universe. And the reason for that is, when you take a charge up and down, first off, moving charges are magnetic. Oh yeah, okay. I mean, it's not just electric field that's here. Yep, this guy makes an electric field when he's sitting still. But if you move him, ooh, now he's a current. And now he makes a magnetic field. And because that magnetic field is changing, because I'm yanking this charge up and down and reversing its direction, the magnetic field is changing with time. And changing magnetic fields are electric. And that electric field changes with time, and it's magnetic. And the magnetic field changes with time, and it's electric, and they make each other. And some of the electric and magnetic field lives around this jostling charge, but not all of it. Some of it actually takes off and heads off across the universe. Nothing will ever stop it. It will go forever. So if you have, in principle, you have you got static charge on your hand, and you go up and down like this, you are making an electromagnetic wave that is going across that will never stop. It'll be there at the forever going off. People can, in principle, detect it and collect it. It's carrying energy with it. They can collect it, but they'll never get all of it. It'll keep on going. All right. So part of the goal of today is to show you how that all works. Why does that happen, and how does it happen? All right, so some observations about radio. They can transmit sound. I mean, the original use of radio was transmitting sound. It can go long distance, and really no wires in between. I mean, you use this now routinely, right? As soon as the bell rings, or before, there's no bell anymore. But you'd be out there communicating, and maybe not sound, but the equivalent of sound. It goes long distances wirelessly. It involves antennas. Whether you can see them or not, there are structures in even your cell phone that are involved in conveying this interaction and receiving it. It apparently involves electricity and magnetism because, in effect, I told you so. And they talk about electromagnetic waves. It sure sounds like it's electric and magnetic. Yeah, sure enough, it is. And you probably observed that where you are matters. Sometimes you get better reception than others. It's getting better as years go by. The old days of you're breaking up. That's kind of passé now, right? They just lose the connection altogether. But it does matter where you are, and even how you hold the phone. The reception certainly weakens with distance. The whole idea of for example, cell phones. The way the cells work is they allow many people to communicate with base stations, the little transmitter receivers to which you're actually interacting when you're using your cell phone. They allow people here in Charlottesville to use the same frequency of interaction, the same very similar waves here as in Crozet or Lynchburg or Richmond. The reason you don't mess each other's communication up is because with distance, the interactions the radio waves get weaker to the point where someone in Richmond can't, the whole system in Richmond is pretty much oblivious to the fact that you are using the same communication stuff here as they're using in Richmond. You're too far away. the brightness of your radio waves is just too dim. You see the same effect with a flashlight. The flashlight's bright when you hold, it's too super bright. But somebody off a mile away looks at the same flashlight beam. It's gotten pretty weak because the beam has spread out both horizontally and vertically, and it's lost brightness by a factor of the distance squared. Same thing happens with radio. A last observation is there are two classic styles of radio. This has been enormously increased over the recent years, but the original ones were AM and FM, which you're still somewhat aware of. The idea here is that radio waves in themselves are just these waves that head off across space. They aren't inherently conveying anything, but if you do stuff like wink them on and off, now you can signal somebody. It's like smoke signals, right? Just smoke conveys no information, but smoke that is pulsed on and off by a blanket, now you can send some information. The same kinds of things are going on with radio. Playing with the radio wave, so it's not constant, allows you to convey information. And the original information that was conveyed was sound information. Subsequently, now everything, the whole internet can come roaring to your phone by way of radio waves. All right. How can a radio wave exist? Is my first choice. And really, it is this idea that we've seen that electric and magnetic fields, first off, they exist. They're real things. They're not a fiction created in order to make your lives more complicated. They're real, and it is possible to make an electric field without charge. How? Play with the magnetic world. And it is possible to make a magnetic field without magnetic pole. How? Play with the electric world. Make it change with time. And so if you can have a changing electric field and a changing magnetic field, as a pair, as a team, they can create one another. And they'll do it endlessly and indefinitely. They'll head off across space. They will not they will not stand still, not unless you confine them, in effect, with mirrors. But if you create them and you arrange them properly and have them change with time properly, they will head off across space at a frightening speed, right? The speed of light. They'll go very fast. But it's a self-sustaining ripple in these two structures in space that I call electric and magnetic fields. Off they go. Is that okay? Let me show you. I'll stop here with this, and I'm taking images out of the figures from the book. What you're looking at here, so the book, I do encourage you to look at the online book because it's got me talking about all these. Oh, I want it to continue. Where's the settings? Play again. Rewind. There we go. What you're looking at here is a wave heading along the yellow line. It's a ripple in the electric and magnetic fields heading to the right. And in this picture, it's heading to the right about as fast as my green pointer is going. The red arrows are showing you the electric field at each point in space. The green arrows are showing you the magnetic field at each point in space. The electric field, say at this point right here, is now pointing downward. Now it's pointing upward. Now it's pointing downward. Now it's pointing up. At the same time, the magnetic field is pointing away from us, toward us, away from us, toward us. And so they're both changing with time. There's an electric field and magnetic field at every point along this line. And we're not paying attention to above or below the line or nearer or farther. Just the line. Electric fields are working as a team. Electromagnetic field, they're working as a team. They live at right angles with each other, and each one is creating the other. And they create this ripple. This is one of many possible ripples. They don't all have to head to the right like this. This one happens to head to the right. And it goes at a certain speed. You see it going by, and it's got a certain spatial distance between the peak upward electric field and the other peak upward electric field. That we'll see. It's called a wavelength. But this structure, there's no charge in this. To create that thing, you needed charge or something like charge. And to receive it, you need charge or something like charge. But once you created it and let it rip, it whizzes across space without any charge, without a magnetic pole. It's the two fields creating each other. And I'll stop there, and we'll look more back at it again on Wednesday.